Hi students, and welcome to this very first chapter, which is progressions. Now there are basically three types of progressions that we are going to study in detail. These are the arithmetic progressions, the geometric progressions and the harmonic progressions. So we have divided this entire chapter on progressions into four parts. The first covers the arithmetic progressions, the second is all about geometric progressions, the third is about harmonic progressions, and the fourth is all about the arithmetic, geometric and harmonic means. In this very first lecture, we are going to study about arithmetic progressions. Here we are going to study what do we mean by an arithmetic progression, what is the general term of such a sequence, then how to find the sum of n terms of an AP. Also, we are going to solve a few problems that will help us to understand all these concepts more clearly. So, let's begin with this very first lecture, which is all about the progressions and arithmetic progressions. In this entire chapter, we are going to study about the different kinds of progressions. But before we go into these different types of progressions, first let's try to understand the meaning of progressions. What do we mean by progressions? Progression, as the name indicates, refers to the act of progressing, that is moving from one element to the next. So, if we have a sequence or a series in which we have got a number of terms or we have got number of elements, then the act of progressing or the movement from one element to the other is known as progression. For example, if we have a sequence S in which these are the terms, it has got n terms, x1, x2, x3, x4, x5 and so on up to xn. Then the act of progressing from one element to the other is known as progression. So we are progressing or moving from one element to the other. So it's possible that these series have some pattern. That is, the elements follow a definite rule. So first of all, let's see what do we mean by pattern over here. Now in our daily lives, we see so many patterns. Like if we look at the honeycomb, then it has got a pattern, it follows a rule. If we look at a pineapple, then we see this spiral follows a particular pattern. Similarly, if we look at a sunflower, you can clearly see that the petals follow a pattern or a rule. And even the grains of a maize cob follow a pattern. So these are some of the examples of things that follow a pattern in our daily life. Let's see one more example, the number of squares. So let us say that this is a square. Number of squares is equal to 1 here. 1 square equal to 1. Similarly, this is a square in which we see 4 smaller squares. So the number of squares here is 2 square, which is equal to 4. Similarly, if we look at this square, then we see that there are in all 1, 2, 3, 4, 5, 6, 7, 8, 9. There are in all 9 squares in this big square. So this is equal to 3 square. So we see here that even these squares follow a pattern or a rule. So these are some of the examples of things or events that follow a pattern or follow a particular rule. Now, how do we move from one element to the next? Is there a rule by which we can tell the given current element and the previous ones in the sequence? What is the next element? Now if we say that we have a series or a sequence, now is there any rule by which we can tell the current element and the previous element? Also, can we tell the next element? Now if we have a rule or a pattern, then we can easily tell the next element or the previous element. But what is that rule? This is something we are going to study under the progressions. So we can say that if we have a sequence, then there are two choices. Either this sequence could follow a fixed pattern or the sequence could not have a fixed pattern. If the sequence follows a fixed pattern, then such a sequence is known as progressions. So progressions are sequence in which the terms or the elements follow a fixed pattern or a fixed rule. Now, what are the different types of progressions? We have just seen what is a progression, but there are different types of progressions, and these progressions are the arithmetic progressions, geometric progressions and the harmonic progressions. So these are the three major types of progressions that we are going to study in this chapter: the arithmetic progressions, the geometric progressions and the harmonic progressions. So one by one we are going to see all these three types of progressions. The first is the arithmetic progressions. Now what are arithmetic progressions? Let us say that we have a series 1, 2, 3, 4, 5, 6 are the elements of the series. Now what we observe, the difference between these two terms is equal to 1. The difference between these two terms is equal to 1. The difference between these two terms is also equal to 1. The difference between these two terms is equal to 1. And so we can say that the difference between the consecutive terms is constant. And this difference here in this case is equal to 1. So this is an example of an arithmetic progression. This sequence 1, 2, 3, 4, 5, 6 and so on is an example of an arithmetic progression. Similarly, let's see one more example. If we have a series 1, 4, 7, 10, 13, 16. Now again, if we look at the difference between these two consecutive terms, then this is equal to 3. Also, the difference between these two terms is equal to 3. The difference between these two terms is equal to 3. The difference between these two terms is equal to 3. And the difference between these two terms is also equal to 3. Again, we can say that the difference here is constant and that is equal to 3. So this is also an example of an arithmetic progression. Now we have seen the two examples of arithmetic progressions. But now let's look at proper definition of an arithmetic progression. So what do we mean by an arithmetic progression? So we can say that an arithmetic progression, or AP short form, is a sequence in which the difference between any term and its just preceding term is constant throughout. This constant is called the common difference of the AP. So we can define AP as a sequence in which the difference between any term and its just preceding term is constant. This constant difference is called as the common difference of the AP. Now, let us say that we have an AP in which A1, A2, A3, A4 and so on up to AN represents the n terms of this AP. Now, the difference between A1 and A2 would be equal to D. The difference between A3 and A2 would be equal to D. The difference between A4 and A3 is equal to D. And so here D is the common difference. We can say that the first term here is A1. The common difference here is equal to D. And the nth term is given by AN. So this is an AP in which the first term is A1, common difference is equal to D, and the nth term is given by AN. Now let's see the formula how to find out the nth term of any AP. So once again, let's take an AP in which the terms are A1, A2, A3, A4 and so on up to AN. Now let us say that A1, which is the first term, is equal to A, and the common difference, that is the difference between the consecutive terms, is equal to D. So here A2 minus A1 would be equal to D. This comes from the definition of an AP. So A2 would be equal to A1 plus D. Now A1 is equal to A and the common difference is D. So A2 would be equal to A plus D. Similarly, A3 minus A2 would also be equal to D. So A3 would be equal to A2 plus D. Now we know the value of A2, which is A plus D. And when we put this value over here, what we get is A3 equal to A plus 2D. Similarly, let's try to calculate the value of A4. Also A4 minus A3 is equal to D. From this we get A4 equal to A3 plus D. And we know the value of A3, which is A plus D. Therefore A4 would be equal to A plus 3D. Thus from all these, what we can conclude is that AN, or the nth term, is equal to A plus n minus 1 into D. Here A is the first term, n is the number of terms, and D is the common difference. So the nth term of an AP is given by A plus n minus 1 into D. Given the nth term of an AP with the common difference D, find the mth term in terms of nth term and the common difference D. So in this problem we have been given the nth term of an AP and the common difference here is D. We have to find the mth term of this series in terms of the nth term and the common difference D. So let's look at the solution of this problem. Let us say that the first term is equal to A and the common difference is equal to D. So let us suppose that the first term is A and the common difference given to us is D. Now the nth term AN would be equal to A plus n minus 1 into D. This comes directly from the formula. So let us say that this is equation number 1. Similarly, the mth term of the series would be given by a plus m minus 1 into d, and let us say that this is equation number 2. Now what we do is we subtract equation 1 from 2, and what we get? We get am minus an equal to m minus n into d. A and a gets cancelled, and what we get in the RHS is m minus n into d. We take an to this side of the equation and get am equal to an plus m minus n into d. Thus we can say that the mth term of this series is equal to the nth term plus m minus n into the common difference, which is d. Let's try to solve one more example. If m times the mth term of an AP is equal to n times the nth term, prove that the m plus nth term of this series is 0. So what we have been given is, we have been given a condition that m times the mth term is equal to n times the nth term, and we have to prove that the m plus nth term of this AP is equal to 0. So once again, let's look at the solution. Let us say that the first term is a and the common difference is equal to d. Now given to us is m times the mth term equal to n times the nth term. Now the mth term am would be equal to a plus m minus 1 into d, and similarly the nth term an would be equal to a plus n minus 1 into d. We get this from the formula for the nth term. So m times a plus m minus 1 into d would be equal to n times a plus n minus 1 into d. This becomes am plus m square d minus md equal to an plus n square d minus nd. Now this further becomes a times m minus n equal to m minus n into d minus d into m square minus n square. Now we can also write m square minus n square as equal to m minus n into m plus n, and so as m is not equal to n, we can cancel this factor m minus n from both sides of the equation. What we get is a equal to d minus m plus n into d. Now further, this equation could be written as a plus m plus n minus 1 into d. We take all these terms to this side, that is the LHS, and get a plus m plus n minus 1 into d equal to 0. Now this is nothing but the m plus nth term, and so we can say that the m plus nth term of this AP is equal to 0. Thus if the mth term is equal to the nth term, then the m plus nth term of such an AP would be equal to 0. Now we know how to find the nth term of an AP, but if I ask you what is the sum of n terms of an AP, then how are you going to find that? So now we are going to look at how to find out the sum of n terms of an AP. Let us say that we have a piggy bank and every year we are putting some money into it. If in the first year we have put 100 rupees, in the second year we put 150 rupees, in the third year we put 200, in the fourth 250, in the fifth year we put 300, and so on. Now if I ask you, after 21 years, what is the amount in the piggy bank? So what would be your answer? What is the total amount that is collected in this piggy bank after 21 years? Simply you are going to add 100 plus 150 plus 200 plus 250 and so on up to the 21 terms. That would be one method. But is there a formula or a shortcut to find the sum of n terms of this AP? That's something we are going to study now. So before we find out the sum of n terms of an AP, let's first try to find out the sum of first 100 natural numbers. Now this is a series S which is equal to 1 plus 2 plus 3 plus 4 and so on up to 100. Now all these are natural numbers up to 100. Now what we do next is we write the same series but in a reverse manner, that is 100 is the first term, 99 is the second term and so on up to 2 and 1. So we have simply written the series in a reverse manner. Now what we observe here is that the sum of this term and this term is equal to 101. The sum of this term and this term is also equal to 101. The sum of 3 and 98 comes out to be equal to 101 and so on. That is, the sum of each and every pair is equal to 101. So if we add them, what we get? 2s equal to 101 plus 101 plus 101 and so on up to 100 times. 100 times because there are 100 such pairs. Now this could be further written as 2s equal to 101 into 100, or we can write s equal to 50 into 101. Now when we multiply 50 and 101, what we get is s equal to 5050. Thus we can say that the sum of first 100 natural numbers is equal to 5050. Now there's something very interesting here. We have found out the sum of first 100 natural numbers. Now this series is also an AP. Here the common difference is 1. So we have taken a special case and found the result of the sum of first 100 natural numbers. Now we are going to see how to find the sum of n terms of an AP. We have any AP and we are going to find out the sum of n terms. Let us say that the first term of this AP is equal to A and the common difference is equal to D. So we take a general AP that first term equal to A and the common difference equal to D. Now, the terms of this AP would be A plus D, A plus 2D, A plus 3D and so on up to A plus n minus 1 into D. This is the nth term. Now let us say that the sum of all these terms is equal to S. So S could be written as A plus D plus A plus 2D plus A plus 3D and so on up to A plus n minus 1 into D. Now what we do is, we write the same sum of the series, but here we have simply reversed it. That is, we have written this term as the first term and all these terms are written in a reverse order. So this becomes A plus n minus 1 into D plus A plus n minus 2 into D and so on up to A plus D plus E. So what we again observe here is the sum of this term and this term is equal to 2A plus n minus 1 into D. The sum of this term and this term also is equal to 2A plus n minus 1 into D and so on up to this term. That is, each and every pair has the sum equal to 2A plus n minus 1 into D. What we do is, we add both these equations and get 2s equal to 2a plus n minus 1 into d plus 2a plus n minus 1 into d and so on up to n times because there are n such pairs. Thus we can further write this as 2s equal to 2a plus n minus 1 into d into n, and this further becomes s equal to n by 2 into 2a plus n minus 1 into d. Thus, the sum of n terms of an AP is equal to n by 2 into 2a plus n minus 1 into d. Your n is the number of terms, a is the first term, and d is the common difference of an AP. So this is the formula for finding the sum of n terms of an AP. Now, the sum of n terms is equal to n by 2 into 2a plus n minus 1 into d. Now we can further split 2a as a plus a and write the sum of n terms equal to n by 2 into a plus n minus 1 into d. Now, we also know that a plus n minus 1 into d is equal to the nth term, which is an. Thus, we can write this as sum of n terms equal to n by 2 into a plus an. An is the nth term. Thus, we can further write this as sum of n terms equal to number of terms divided by 2 into first term plus the last term. Thus, one more formula of finding the sum of n terms is n by 2 into a plus an, where an is the last term of the AP. Again, let's go back to the piggy bank problem. The amount after first year is equal to 100, amount after second year is equal to 150, amount after third year is equal to 200. Now this forms an AP. And here we see that the first term is equal to 100, D is equal to 50, and n is equal to 21 because we have to find the sum after 21 years. So n would be equal to 21. Now simply what we are going to do is, we are going to apply the same formula for finding the sum of n terms of the AP and get the result. So S of 21, that is the sum for 21 terms, would be equal to 21 by 2 into 2 into 100 plus 21 minus 1 into 50 because the formula is n by 2 into 2a plus n minus 1 into d. So simply substitute the values of a, d and n over the formula to get this expression. This further becomes 21 by 2 into 200 plus 1000, which becomes 1200, and so the answer would be the sum after 21 years is equal to 12,600 rupees. So simply the amount in the piggy bank after 21 years would be 12,600. Now based on the sum of n terms of an AP, let's try to solve a few examples to understand this formula more clearly. If the sum of the n terms of an AP is 3n square plus 5n by 36, then the common difference would be, so in this problem we have been given the sum of n terms in terms of n, and we have to find out the common difference of such an AP. So again, let's look at the solution of this problem. Given to us as Sn, which is the sum of n terms, equal to 3n square plus 5n by 36. Now what would be the nth term? We can simply write the nth term as the sum of n terms minus the sum of n minus 1 terms. So Tn would be equal to Sn minus S of n minus 1. Now to find S of n minus 1, what we do is we simply substitute n by n minus 1 in this equation to get the value of S of n minus 1. So Tn would be equal to 3n square plus 5n by 36, which is Sn, minus 3 of n minus 1 whole square plus 5 into n minus 1 whole divided by 36. This is S of n minus 1. This further becomes T of n equal to 3 into 2n minus 1 plus 5 divided by 36. Now this is the general term or the nth term of such an AP. So what we are going to do is we are going to find the second term and the first term and subtract them to get the common difference. Now T of 2, which is the second term, would be equal to, we simply put T equal to 2 in this expression to get 3 into 2 into 2 minus 1 plus 5 divided by 36, which comes out to be equal to 14 by 36. Similarly, we are going to find the first term by simply substituting n equal to 1 in this expression. So T of 1 would be equal to 3 into 2 minus 1 plus 5 divided by 36, which is equal to 8 by 36. So the common difference in this case would be T2 minus T1, which is 14 by 36 minus 8 by 36, which comes out to be equal to 6 by 36, and this could be further written as equal to 1 by 6. Thus the common difference of this AP comes out to be equal to 1 by 6. Now let's solve an IIT problem. This problem appeared in 1980, and what does it say? It says that the interior angles of a polygon are in the arithmetic progression. The smallest angle is 120 degrees and the common difference is 5 degrees. Find the number of sides. So in this problem we have been given that the interior angles of a polygon are in arithmetic progression. Also, the smallest angle is equal to 120 degrees and the common difference is equal to 5 degrees. And we have to find out the number of sides. So how are we going to proceed? Let's once again look at the solution of this problem. Now let us say that the number of sides is equal to n. Now we also know that the sum of all the angles of a polygon are given by the formula n minus 2 into 180 degrees. So the sum of all the angles of any polygon of n sides is equal to n minus 2 into 180 degrees. Now also given to us is that the angles are in AP and the first term is 120 degrees and the common difference is 5. So the sum of all the angles would be equal to n by 2 into 2 into 120 degrees plus n minus 1 into 5. Here A is equal to 120 degrees and the common difference is equal to 5. So we get this expression. Equating 1 and 2. Now this is the expression for the sum of all the angles of a polygon with n sides, and this we have found by using the condition that the angles are in AP. So the sum would be the same, and so we can equate 1 and 2. When we equate 1 and 2, what we get is 180 into n minus 2 equal to n by 2 into 240 plus 5n minus 5. This further becomes 360n minus 720 equal to 240n plus 5n square minus 5n. This could be further written as 5n square minus 125n plus 720 equal to 0, or n square minus 25n plus 144 equal to 0. Now this is a quadratic equation, and so we can further factorize this as n minus 16 into n minus 9 equal to 0. So we have simply factorized this quadratic equation into two factors, n minus 16 into n minus 9 equal to 0. And so from this what we get is n could either be equal to 16 or it could be either equal to 9. So we get two values of n. N could be either equal to 16 or n could be equal to 9. Thus, using the concept of sum of n terms of an AP, we have solved this IIT problem. Now, selection of n terms in an AP. Now if we have an AP and we have to select any n terms, then how are you going to select such n terms? Now this is a table that helps us to select n terms in an AP. Now if in the problem it has been given 3 terms, then the terms that we could select are a minus d, a and a plus d. If the common difference of this AP becomes equal to d. Now if we have to select 4 terms, then what are the terms you are going to select? We can select them to be a minus 3d, a minus d, a plus d and a plus 3d, and so the common difference becomes 2d. Similarly, if we have got 5 terms, then we will select terms as a minus 2d, a minus d, a plus d and a plus 2d, and here the common difference is d. And if we have to select 6 terms, then we should select them as a minus 5d, a minus 3d, a minus d, a plus 3d and a plus 5d, and the common difference becomes 2d. Now why we are doing so? Why we are selecting such terms? The reason behind this is, if we add all these terms, we see that d gets cancelled and what we get is the sum only in terms of a, and that makes the problem very easy to solve. Similarly, if you look at all these 4 terms and add them, d gets cancelled and it becomes 4a. That is, the sum is only in terms of a, and so again the problem becomes very easy, and that is the reason why we select such terms. Now let's see some of the very important properties of an AP. So the first property is, if a constant is added or subtracted from each term of an AP, then the resulting sequence is also an AP with the same common difference. So this property says that if we have an AP and if we add or subtract the same term to each and every term of the AP, then the resulting sequence is also an AP, and even the common difference remains the same as the original one. Let's try to understand this. Let us say that we have an AP 1, 4, 7, 10, 13, 16. Now what's the common difference? Of course, the common difference is equal to 3. Now what we do is, we add 2 to all the terms. So if we take a number 2 and add 2 to all these terms, what we get? We get the term as 3, 6, 9, this becomes 12, this is 15 and this becomes 18. Again, if we try to see the common difference, then what we get is 6 minus 3 is equal to 3, 9 minus 6 is equal to 3, 12 minus 9 is also equal to 3, and so we can say that the common difference is equal to 3. The common difference of this sequence was also 3 and the common difference of this sequence is also 3. So it proves that if we add a same number to all the terms of an AP, then the resulting sequence is also an AP and the common difference also remains the same. Now what we do next is, we subtract 2 from all the terms of this AP. So what we get? This becomes minus 1, this becomes 2, this becomes 5, this becomes 8, this becomes 11 and this becomes 14. Now the common difference again becomes 3. Why? Because 2 minus minus 1 is equal to 3, 5 minus 2 is equal to 3, 8 minus 5 is equal to 3, and so we can say that the common difference is equal to 3 again. So again, if we subtract a same number from all the terms of an AP, then the resulting sequence is also an AP and with the same common difference. And so we have proved the first property. Let's look at property number 2. And what does it say? It says that if each term of a given AP is multiplied or divided by a non-zero constant k, then the resulting sequence is also an AP with the common difference k into d or d by k, where d is a common difference of the given original AP. So this property says that if we multiply or divide a given AP by a non-zero constant k, then the resulting sequence is also an AP, and here the common difference becomes k into d, that is k times the common difference, or d by k, where d is the common difference of the original AP. So let's try to understand this property. Again, we take the same AP as 1, 4, 7, 10, 13, 16 and so on. Now we multiply all the terms by 2. So what we get is, we get this term becomes 2, this becomes 8, this becomes 14, this becomes 20, this becomes 26 and this becomes 32. Now what is the common difference of this sequence? Here it is 8 minus 2, which is 6, 14 minus 8 is also 6, 20 minus 14 is also 6 and so on. Thus a common difference here becomes equal to 6. But 6 is nothing but 2 into 3. 3 was a common difference of this sequence. Thus we can say that common difference is equal to 2 into 3, which is equal to 6. And so we can say that if we multiply all the terms by a same number, then the common difference of the new sequence becomes k times the original common difference. Similarly, let's divide all the terms by 2. What we get, the sequence becomes 1 by 2, 2, 7 by 2, 5, 13 by 2, 8. Now, if we find the common difference for this sequence, then this would be 2 minus 1 by 2, which is equal to 3 by 2. 7 by 2 minus 2 is equal to 3 by 2. 5 minus 7 by 2 is also equal to 3 by 2. Thus, we see that the common difference would be 3 divided by 2. Now, 3 was the common difference of this series, and we have divided all the terms by 2. So, we can say that the common difference of the new sequence becomes t by k. Thus, we can say that if we multiply all the terms of an AP by a number k, then the common difference becomes k times t. And if we divide all the terms by k, then the common difference of the new sequence becomes t by k, where d is the common difference of the original AP. Now let's try to understand the property number 3. It says that in a finite AP, the sum of the terms equidistant from the beginning and the end is always the same, and this is equal to the sum of first and the last term, that is a of k plus a of n minus k minus 1 is equal to a1 plus an for all k equal to 1, 2, 3 up to n minus 1. So this property says that in a finite AP, the sum of the terms equidistant from the beginning and the end is always the same, and this is actually equal to the sum of the first term and the last term. So let's try to understand this. Now let us take an example. We have an AP in which the first term is equal to a, the common difference is 3, and the number of terms is equal to 8. So the terms become 1, 4, 7, 10, 13, 16, 19 and 22. Now the sum of the first and the last term is equal to 23. Similarly, the sum of the second term and the seventh term is equal to 23. These two terms are actually equidistant from the beginning and the end. Similarly, the sum of third term and the sixth term is equal to 23, and also the sum of fourth term and the fifth term is equal to 23. Thus we see that the sum of this term and this term is equal to 23. The sum of second term and seventh term is equal to 23, and both these terms are equidistant from the beginning and the end. This is the second term from the beginning, and similarly this is the second term from the end. Similarly, the third term and the sixth term, which are equidistant again from the beginning and the end, is equal to 23, and the sum of fourth term and the fifth term is also equal to 23, and the sum is actually equal to the sum of the first term and the last term, which is equal to 23. Thus we can say that if we have an AP, then the sum of the equidistant terms from the beginning and the end is always the same, and this is actually equal to the sum of the first term and the last term. Let's look at property number 4, and this property says that the numbers a, b, c are in AP if 2b is equal to a plus c. So this property says that if we have got three numbers a, b, c, and if these three numbers are in AP, then the relation between a, b and c would be 2b equal to a plus c. Again, let's try to understand this. If we have a sequence 1, 4, 7, 10, 13, 16. Now, if you take the numbers 1, 4, 7. So we have taken the numbers 1, 4, 7, and let us say that a is equal to 1, b is equal to 4, and c is equal to 7. Now, 2 into 4 is equal to 1 plus 7, 8 equal to 8. Thus, we see that twice of the second number or the middle number is equal to the sum of the first number and the third number. Thus, we can say that 2b is equal to a plus c. Thus, for these three numbers which are in AP, we have proved that 2b is equal to a plus c. Similarly, we take the numbers 7, 10 and 13. We take these three numbers. Again, we take a to be equal to 7, b to be equal to 10, and c to be equal to 13. Now, twice of the second term would be 20, and the sum of 7 plus 13, which is the first and the last term, is equal to 20. So 20 equal to 20, and thus we can say that 2b is equal to a plus c. Thus, if we have got three numbers which are in AP, then they are connected by the relation 2b equal to a plus c, where a is the first term, c is the third term, and b is the second term. Let's look at property number 5, and it says that a sequence is an AP if its nth term is a linear expression in n. That is, an is equal to an plus b, where a and b are constants. In such a case, the coefficient of n in an is the common difference of ap. So this is a very important property, and it says that if we have a sequence such that the nth term is given by a linear expression, and this linear expression could be an plus b, then such a sequence would be an AP, and the common difference of such an AP would actually be the coefficient of n in the expression of an. That is, a would be the common difference. So let's try to prove this. Let us say that an, which is the nth term, is equal to an plus b. Now a of n plus 1 would be a times n plus 1 plus b. Simply replace n by n plus 1 in this expression to get the value of a of n plus 1. Now a of n plus 1 is given by this expression, and a of n is given by this expression. What we do is we subtract this equation from this to get a of n plus 1 minus an equal to an plus a plus b minus an minus b. Now what we observe in the RHS is an and an gets cancelled, b and b gets cancelled, and what we get is a. Thus a of n plus 1 minus an is equal to a, and so we can say that the common difference of this AP is equal to a, and this is a constant and it does not depend on the value of n. Thus we can say that the sequence is an AP and the common difference is equal to a. Also, a is the coefficient of n in an. Here this is the expression of an, and we see that here a is the coefficient of n. So once again we can say that if we have a sequence such that the nth term is given by a linear expression an plus b, then the sequence is an AP, and the common difference of this AP would be the coefficient of n. Let's look at property number 6, and this property says that a sequence is an AP if the sum of its first n terms is of the form of an square plus b, where a comma b are constants independent of n. Also, in such a case, the common difference is 2a, that is 2 times the coefficient of n square. So this property says that if we have a sequence such that the sum of the first n terms is of the form of an square plus b, where a and b are constants independent of n, then such a sequence would be an AP, and the common difference of this AP would be 2 times the coefficient of n square. So again, let's look at the proof of this property. Let us say that the summation of n, that is the summation of n terms, is equal to an square plus b. Now summation of n minus 1 terms of the sequence would be a into n minus 1 whole square plus b. Simply replace n by n minus 1 in this expression. Now summation of n minus summation of n minus 1 would be equal to an square plus b minus a times n minus 1 whole square plus b. This is nothing but the nth term. Summation of n terms minus the summation of n minus 1 terms is always equal to the nth term. So a of n would be equal to an square plus b minus a times n minus 1 whole square plus b. When we further solve it, what we get is 2 times an minus a. We can also write this as a times 2n minus 1. Thus an is equal to 2an minus a. Now a of n minus 1 would be, now let's try to find out the n minus 1th term. This would be equal to a into 2 times n minus 1 minus 1. Simply what we do is we replace n by n minus 1. So this becomes 2an minus 3a. Thus an, the nth term, is equal to 2an minus a, and the n minus 1th term is equal to 2an minus 3a. Now the nth term minus the n minus 1th term is equal to, we subtract both these equations, and what we get is 2a. Thus this is a constant, it does not depend on the value of n, and so we can say that this is an AP with a common difference equal to 2a. Also a is actually the coefficient of n square. Thus we can say that if the sum of n terms is given by the expression an square plus b, where a and b are constants, then such a sequence is an AP in which the common difference is equal to 2 times the coefficient of n square. Now let's try to solve a few IIT problems based on the concepts of arithmetic progressions. So the first problem is, if the sum of the first 2 n terms of the AP series 2, 5, 8 and so on is equal to the sum of first n terms of the AP series 57, 59, 61 and so on, then n is equal to, and we have been given the 4 options. The first is 10, B is 12, C is 11 and D is 13. So in this problem we have been given two AP series and the condition is the first two n terms of the first AP is equal to the first n terms of the second AP, and we have to find the value of n, and four options have been given to us. So let's look at the solution of this problem. Given to us is S of 2n equal to S dash n, that is the sum of first two n terms of the first AP is equal to the sum of n terms of the second AP. Now let's first find out the value of S of 2n, that is the sum of 2n terms of the first AP. This would be equal to 2n by 2 into 2 into 2 plus 2n minus 1 into 3. Why? Because your A, that is the first term, is equal to 2 and D, which is a common difference, is equal to 3. Therefore this becomes n into 4 plus 6n minus 3, which further reduces to n into 6n plus 1. Thus the value of S of 2n comes out to be equal to n into 6n plus 1. Similarly, let's try to find out the value of S dash n, which is the sum of first n terms of second AP. This is again equal to n by 2 into 2 into 57 plus n minus 1 into 2. Your A is equal to 57 and the common difference is equal to 2. This further becomes n into 56 plus n. Thus the value of S dash n is equal to n into 56 plus n. So from this, what we do is we equate both these expressions. 6n plus 1 into n would be equal to 56 plus n into n. N and n gets cancelled, and what we get is 6n plus 1 equal to 56 plus n. This further becomes 5n equal to 55 or n equal to 11. Thus the value of n is equal to 11, and so we can say that option number C is correct. So just using the concept of sum of n terms of an AP, we have solved this IIT problem. Let's see another problem, and this problem appeared in IIT JEE 2000. It says that the fourth power of the common difference of an arithmetic progression with integer entries is added to the product of any four consecutive terms of it. Prove that the resulting sum is the square of an integer. So in this problem, what we have given is that the fourth power of the common difference is added to the product of any four consecutive terms of it. We have an AP and in which the fourth power of common difference is added to the product of any four consecutive terms. We have to prove that the resulting sum is the square of an integer. So let's again look at the solution of this problem. Let us say that the four consecutive terms of the AP are A minus 3D, A minus D, A plus D and A plus 3D. We have earlier seen that if we have to take four consecutive terms of an AP, then we choose them as A minus 3D, A minus D, A plus D and A plus 3D. Here the common difference is equal to 2D. We have taken an AP in which the common difference is equal to 2D, and thus these are the four consecutive terms of this AP. Now the product of all these four terms would be equal to A minus 3D into A plus 3D into A minus D into A plus D. Also, the fourth power of common difference would be equal to 2D to the power of 4, which is equal to 16D to the power of 4. Thus, this is the fourth power of common difference and this is the product of these terms. Now we have to prove that the fourth power of the common difference plus the product of these terms, these four consecutive terms, is equal to the square of any integer. So let's say that S, which is the sum of these two terms, is equal to 16D to the power of 4 plus A minus 3D into A plus 3D into A minus D into A plus D. This further becomes S equal to